Section 4.2 is about straight line motion, and you are going to calculate rates of change in applied contexts. There's also quite a bit of vocabulary in this section. And I just really want to emphasize that all of the motion here is incredibly boring. You're always going to move completely on a straight line, either on the x-axis or the y-axis. You will not be moving randomly around. You won't be, taking a path. You're just going to be going in a straight line for all of this. In chapter, I think it's 9 this year, we'll start moving around the plane. Right now, straight line. That's it. So first of all, the definition of position. The position is just your location at a given time. If you are traveling horizontally, your position is an x of t function. I want to really emphasize that in that case, the t coordinate is the independent variable and the x coordinate is the dependent variable. If you're traveling up or down, it would be y of t. And if you're just traveling in a straight line, but it's not really, doesn't matter whether it's horizontal or vertical, then we usually call it s of t. S for straight line. I don't love s of t because it looks like a 5, but it is used sometimes. The units for position would be distance units, like feet, meters, miles, or something like that. Your independent variable is t, so if you take a derivative with respect to t, like t is your independent variable, then you get a change in position divided by a change in time. So it'd be like dx dt. And dx dt, or dy dt, is velocity. So when you take a first derivative, you get the rate of change of your position, which is velocity. And so that's the first derivative of those position functions. Sometimes we call it v of t, sometimes we call it x prime of t. The units, because it would be a change in distance over a change in time, would be feet per second, meters per minute, etc. Some like vocabulary stuff, the sign of velocity, like you can have a negative velocity. We think of velocity and speed being the same thing, but the sign tells you whether you're going forwards or backwards, and the magnitude tells you your speed. So I can have a velocity of -3 meters per second, and that just means I'm going 3 meters per second, but I'm going backwards. If it's on the x-axis, that would mean I'm going to the left. If it's on the y-axis, it would mean I'm going down. So speed is the absolute value of velocity. You take the sign off and you just look at the magnitude. So it doesn't tell you how fast it doesn't tell you the direction that you're traveling, it just tells you how fast you're going. Same units as velocity because we didn't really do anything except absolute value, so it would still be feet per second or meters per minute. The second derivative of position is acceleration, and that's the derivative of velocity, or sometimes called a of t. It tells you the rate of change of your velocity. And the units are feet per second per second. Sometimes we write that as feet per second squared, or meters per minute, or meters per minute squared, or meters per second squared. Those are your acceleration units. So acceleration tells you how your velocity is changing. Acceleration can be positive or negative. If it's positive, it means that your velocity is increasing. If it's negative, it means your velocity is decreasing. Increasing velocity doesn't necessarily mean you're speeding up. Speeding up has to do with speed. It doesn't have to do with velocity. So if your velocity is -3, let's say, and it increases to -1, you actually slowed down. But your acceleration would be positive because your velocity is getting, so let's write this as meters per second so you get some units on there. This is not an acceleration, this is velocity. If your velocity changes from -3 meters per second to -1 meters per second, then your acceleration would be positive because your velocity numbers are getting bigger, but you're slowing down because you're going 3 meters per second backwards to 1 meter per second backwards. We'll do more examples with that, but I wanted to emphasize it at this point. All right, so just intuitively, we're going to make a sketch of, we're going to pretend that this roller coaster is going, and we're going to make a sketch of what it would look like. So this roller coaster, it starts out fairly high, and then you know how roller coasters go very slowly up the hill? So it's going to go very slowly up. And then there's a time at the top of the hill where it kind of stops and just hangs out for a little bit. And then it comes crashing down. Then it might slow down a little bit here, and then it might go slowly up, and then maybe a little crash down again. It looks a little bit like I'm sketching the track here, but I want you to be aware that the my x-axis is not horizontal distance, my x-axis is time. So even though this is not a terribly steep line, my velocity graph, my position graph would be steep because my position is going to change more quickly as I go down. So anyway, all of this position is positive because you're always up above the ground when you're on a roller coaster. So the uphill portions are showing you speeding up, showing your velocity is, oh, this is position, not velocity. So the uphill portions, you are going in the positive direction. You're going up if I'm looking at height. And the ones with downhill slopes, the velocity would be negative. That doesn't mean, so that would mean that you are going backwards, you're going down, but it's steep, so that means that it's faster. It's downhill steep, but it's going faster. Okay. So here's an example. If a rock is thrown upwards on Mars, its height in meters after t seconds is given by y of t equals 10t minus 1.86 t squared. What is the velocity after 1 second? So velocity is the first derivative, so I'd take a first derivative here, so I'd get 10 minus 1.86 times 2. What is that? 3.72 t. So after 1 second, if we put a 1 in here, we get 10 minus 3.72, so 6.38, no, 6.28. And the correct units for that would be meters per second. The acceleration after 1 second, so I'd need a second derivative. If I take the second derivative, I get negative 3.72. That's just the acceleration on Mars, so it'd be negative 3.72 meters per second squared. And the reason I didn't need to use my 1 second was because the acceleration is not variable. It always is the same. When does the rock reach its highest point? So the rock is going upward, and then it turns around and goes down. And when it goes down, it means that the velocity is negative. So the way that we can tell when it reached its highest point is we're going to check when is the velocity equal to 0. So we're going to do 0 equals 10 minus 3.72 t, and we'll solve for t. And I would need a calculator, so negative 10 divided by negative 3.72, whatever that is, tells me when it reaches its highest point. What is the rock's acceleration when it hits the ground? Well, the acceleration is always 3.72 meters per second squared, but are you curious about when this rock would hit the ground? If you are, you would want to go to the position and set the position equal to 0. So if I do that, I'd have t times 10 minus 1.86 t, and so the rock is going to start on the ground, so t equals 0, you're at the ground, and then the other time that it hits the ground would be when this is equal to 0. I don't really have to figure that out because acceleration is always the same thing, so I don't have to know when it hits the ground. But if you're curious about when it hits the ground, that's how you would solve that. Okay, so I mentioned that speed can sometimes be confusing, so we're going to look at this velocity graph. This is not a speed graph, this is a velocity graph. And the first question is, what is the particle's speed at t equals 35? So speed is the absolute value of velocity. The velocity is negative 20, so the speed is 20 meters per minute. Speed is just how fast you're going, not direction. What is the particle's acceleration at t equals 35? Well, acceleration would be the slope of this velocity graph, so 20 would be the rise, and the run would be 10. Nope, it'd be 5. So 20 over 5, and that would be meters per minute squared. You might also call that 4. Oh, but it's a downhill line, so it's actually negative. And then the other question is the particle slowing down or speeding up then? And you might say, well, it's got a negative acceleration, so it's slowing down. And that's a danger because this particle is actually getting faster. It's going from having a speed of 20 to, like, if you go right here, its speed would be 40. So the particle is speeding up. One way to think about that is if we make a sketch of the speed graph. The speed graph is the absolute value of velocity. So to sketch the speed graph, we would just take all of our values that are below the x-axis and flip them up. All the values that are already above the x-axis, we can leave them where they are. But anything that's below the x-axis, we would sketch so that it's above the x-axis. Now if I go to t equals 35, this is an uphill line, so that is a speeding up point on the graph. That's one way to think about it, with slope as determining whether you're speeding up, but it's the slope of the speed graph, not the slope of the velocity graph. The other way to think about speeding up versus slowing down is if the sign of velocity is negative and acceleration is negative, if they match, then the particle is speeding up. If the sign is different, if the velocity is negative and the acceleration is positive, then your particle is actually slowing down. So in this area, my particle is going from having a speed of 40 to having a speed of 0. My velocity is getting closer to that t-axis, so it's getting closer to 0 at this point. Here my velocity is negative and my acceleration is negative, and so this particle is speeding up because it's going from having a speed of 0 to having a speed of 40. I feel like the ones that are above the x-axis just make more sense. Velocity and acceleration are both positive. Particle is speeding up. Particle is at rest. No, it's not. Particle is not changing. The velocity is not changing. It's not at rest. It's at 60. But then here, the particle is slowing down and the slope is downhill. All right. That's a lot of vocabulary. And that is straight line motion. Your object is moving along a straight line, and you have to understand speed, velocity, and acceleration and position. Thank you.